Hi, my name's Hayden. This is day 10 of doing Leetcode until I get a job. This is Leetcode 1123, lowest common ancestor of deepest leaves. Let's get into it. So this is the medium difficulty problem, and we're given the root of a binary tree. We want to return the lowest common ancestor of its deepest leaves. Note that the node of a binary tree is a leaf if it has no children, so in our case, all of these leaves are children, or are leaves, sorry. Alright, the depth of the root of a tree is 0, alright? And the depth of a node D is the depth of each of its children is +1, okay? So if these are all leaves, and then we're going to have a little number line here, these are the depths. So at each level, they're assigned these depths. So 3 has a depth of 0, yada, yada, yada. All right, cool. And then also the lowest common ancestor of a set of nodes is the node A with the largest depth, such that every node in S is a subtree with root A. Okay, let's unpack that. So basically, what we're trying to find, the lowest common ancestor with the largest depth, is going to be the subtree which contains all of the deepest leaves in the subtree with all the deepest leaves in the full tree. So in our case, the deepest leaves we have are all at level 3. So it's these 2 leaves. If we wanted to find the lowest common ancestor, it would be the small or the deepest parent, which has all of these nodes in it, all of these deepest leaves. So in this case, the first parent when we go up is going to be our answer because it contains all of our deepest nodes. All right. So hopefully that makes a little sense. If we were to say add another element here, now we would have these subtrees, and if we iterate up, we want to figure out where they'd meet. So if we iterate up from this one, we iterate up from this one, iterate up from this one, they all meet at 3. So this is kind of the logic that we're going to be applying, but we're going to do it in an intelligent way that uses as little memory as possible. So the first thing I kind of do when I look at these problems is, first of all, I set these depth values. So we see 0, 1, 2, 3 for our depths. And then especially with these like lowest common ancestor and these kind of traversal problems, it's usually a good idea for each node to place down the depth of its subtree. So for example, the depth of the subtree of 6, the depth of the subtrees on either side of 6 are going to be 0 and 0. So 0 for the left subtree and 0 for the right because it has no subtrees. So I'm just going to do this for all the nodes because usually this information is going to be useful and important. So all the leaves are going to have values of 0, 0 because they have no subtree. And then once we get to, say, node 2, this one's going to have a different value. Instead of being 0, 0, we're going to take the max of the 2 children elements, so 0, 0, and add 1 to it. So the depth of the left subtree on 2 is going to be the max of 0, 0 plus 1, so 1. Right subtree is also going to be 1. All right, and then for 5, we'll do the same logic. For the left element, it's going to be the max of these 2. All right, it's going to be 1 again. Max of 0 plus 1 is 1, and then the max of 1 is 1, and then we're going to add 1, so 2. So this one has a left subtree depth of 1 and a right subtree depth of 2. Okay, and then let's come over here. This one's going to be 1, 1 also, and this one, and the root we're going to have is going to be max of these 2 plus 1. That's 2 plus 1, 2. All right. Looking at this, how can we kind of determine what the lowest common ancestor is with this data? We actually have essentially all we need. So one observation I'm going to make is we already know the answer to this problem. It's going to be kind of this triangle right here. Oops. So with this triangle, let's think of ways of how we would answer it. All right, so we look and see, is there anything special? Is there anything special that we notice? Well, another thing that we can notice is that if there is a subtree which contains, or our lowest common ancestor is going to have a special property, and that's that its depth for the left and right side should always be equal to each other. And what do I mean by that? Let's look at 3, 2 up here. We know this won't be the deepest, the lowest common ancestor because they have different depths. That means that one side is deeper than the other, and thus that can't be the lowest common ancestor, because we can come down the tree. We can come down the tree this way a few times and see that the lowest common ancestor should always have an equal depth for the deepest leaves. So that's kind of strange to explain, but because these are unequal, that means that there's an inefficiency somewhere in the tree, and it cannot be this. So the first condition that we have is left depth must equal right depth. Left depth must equal right depth. And actually, we'll type this out. All right, the first thing we notice is that left depth should equal right depth. Left depth should equal right depth. All right, is there another thing that we notice? Oh, another thing that we notice, right? Not only that the 1, 1 should be, or left and right depth should be equal to in a subtree, we also notice that, although it doesn't show in this example, say that, actually, yeah. So the second thing that we'll kind of notice is that the depth, these subdepths, so we already are assuming they're equal. The depth, or the depth of this tree should be plus the depth that 2 is in the tree, so 2 should be equal to the total max depth, which is 3. So what I'm saying here is that at any node in any level, the depth of the subtree should go down to the deepest depth. So in this case, 1. So 2 plus 1 equals 3. So depth of subtree should extend all the way down to the bottom of the whole tree. And this is going to be depth plus subtree depth plus curve depth equals max depth. All right. Now, with that information, we're going to have to come up with a third condition. But actually, these two conditions are essentially all we'll need. So let's kind of solve this problem using this condition, right? So because this is a binary tree problem, we're probably going to have to do a recursive search through this tree. So the first thing that we're going to do is we're going to explore left. All right, cool. And then we're going to explore left again. And we're going to keep exploring left until we see a null node element. So we explore left, explore left, explore left. And when we're exploring left here, nothing's here. So we're going to want to return this value right here. 0, the 0 for the subtree size. All right, and then we're back at 6. We're going to want to, we're going to want to explore the right subtree. So we explore the right subtree. It's a null. We return 0. After we do this, we're going to want to check our conditions. And we're also, while doing this, we're keeping track of the depth. So not only this, we're going to assign a depth variable somewhere around here so that we get these values like this. All right. We have the cur depth. We're also keeping track of the deepest depth. Okay. I see this and I'm like, okay, well, so far our deepest depth is 2. All right, cool. And our left depth and right depth equal. At the moment, this is our LCA. So right now, LCA equals 6. And in addition to this, I'm going to keep track of the depth that we found it at. So that's our LCA. And the deepest depth right now is equal to 2. This is important because if we find a new deepest depth, this LCA is immediately invalidated. So what do I mean by that? If I'm at a current depth 2 and then I come around and explore these nodes and I find these depth 3 nodes, this cannot be our LCA because this is not containing the deepest leaves. So that's why we're keeping this depth that the LCA is at, our current LCA. Okay, so that's our current LCA. I'm going to explore back up to 5. I want to explore right now. All right, let's explore left. Let's explore left, 0, 0. And we're going to continue this kind of recursive pattern. And while we're here, we do 7, 0, 0. And we see, oh, this is our new deepest depth, 3. Okay, and then we're going to have a new LCA because these left and right subtrees are equal. So the new LCA is node 7 at depth 3. Okay, we come back up to 2, do the same thing for 4. Because 4 is not deeper than 7, nothing really happens. But we do end up returning, like we said, the left and right depths of these subtrees. And at 2, we see that our depths are equal to each other, left and right equal right depth. The depth of the subtree extends all the way down to the bottom of the whole tree. So the current depth we're at 2, plus either one of these because they're equal depth, plus 1 equals 3, which is our deepest depth. All right, so 2 also satisfies our conditions. So do we want 2 to be our new LCA? Yes, we do. So our third condition is going to be choose the highest parent, or we'll say ancestor that satisfies these, what would I call this? These traits. Okay. All right. So because 2 is higher than 7 and 4, we're going to choose that one because it's technically a higher ancestor, and if it's equal and its subtrees are like this, that means that it contains all of the deepest leaves. So our new deep LCA is going to be 2, and it's at 2. All right, cool. This was the new highest ancestor that satisfied the above 2 traits. We're going to go through. We return the depth of our subtrees to 5. Nothing happens, and then we're going to go through, and then nothing else happens. The reason that we have to choose the highest ancestor that satisfies these traits is because we want the common ancestor. That was a little bit of a poor explanation, but let's just hop into the code. It's easier when you see code, in my opinion. So this is, like I said, a recursive solution, and I'm going to solve it with a helper function. It's going to take a tree node and then the current depth we're at. Okay, and that depth was marked over here. Okay, so the first thing we're going to do, if the node is none, we're going to return 0. So all that is this part. We try to explore left on a node with no left node, or it's going to be 0. All right, cool. And then if the depth is deeper than the deepest depth, we're going to actually set the new deepest depth, which is self.lca, and then we're also going to set the LCA to none. This is because in this example, remember, we found a new deepest depth at 7 after we had set 6 as our LCA, but 7 was deeper. That means that 6 does not contain the deepest element. Ergo, it's invalid. So we have to set it to none again. All right. And then we're going to get the left depth and the right depth. Note that we increment depth as we go down the tree. All right, and then we have to check our 3 conditions. All right, does the left and right depths match? Here we go. All right, do the branches go to the bottom? So this is the second one. Depth of the subtree should extend all the way to the bottom of the whole tree. Okay. And then our third condition is higher than ancestor. If self.lca is none, or depth is less than self.lca1, which is the depth of the LCA as we defined here. As we defined here in this part, this is depth. And this is LCA. If all these are true, so if the left and right and the branch goes to the bottom and is a higher ancestor, we're going to set a new LCA at the current depth. And then this is going to return that integer that represents the depth of the subtree. So this actually returns, our function returns this value right here, this 1. And then we call this on the root, and then we just return the self.lca 0. Oh, network error. Well, this passes. I won't be showing this. Oh, okay. Well, trust me, it works. Trust me, bro. All right, till next time. Oh, and by the way, that solution that we had, actually, okay, so it'll have a runtime of O of n, where n are all the nodes in the tree, but it's going to have a space complexity of O of E, or no, O of D, where D is the depth of the tree. And this is because we're doing a depth first search. So this is a DFS search along the tree. And the longest that we'll ever have our stack trace of recursive calls is just going to be to the deepest node. So for example, depth first search is just going to go like this. All right. So this is the stack trace at 6. But if we come up to 5, 4, 2, 1, the stack trace is only ever 4 long, which is the depth of the tree. So it has a time of O of n and a space of O of, actually I'll call it the height. That's a little bit better. All right, and this was Leetcode 1123, lowest common ancestor of deepest leaves.